All right, we're recording. I'm working on your exam. They should be done by today, this afternoon. I graded 4 problems, so I still have 4 to do. Remember last time we had xn plus 1 equal axn, and let's assume xn naught equal to x naught. So we got phi I equal vi lambda I to the n. So this is a column. V is the eigenvector. This is the eigenvalue. Okay? So phi was computed as the column of phi 1, phi 2, phi k, the column. You see that? And we showed that each column satisfies this one here. That way, if we take the first column, we have phi 1 n plus 1 equal a phi 1. And we did verify this. All right. So let me add the following. So then the solution, let's say this is a star, then the solution of a star is xn equal phi n times some constant c, and this is a constant vector. A constant vector. Now, using xn naught equal x naught, we get xn naught equal phi n naught times c, or x naught equal phi n naught times c, multiply both sides by phi inverse of n naught. So we get from the right, sorry, from the left. So we have phi inverse of n naught x naught equal phi inverse of n naught phi of n naught times c, and that is I times c, and that is c. So what is c? So c is phi inverse of n naught x naught. So now let's put it here. So if I come back to here, then xn is phi n phi inverse of s naught x naught. Okay? That is the solution. So we define a n minus n naught to be equal to phi n phi inverse of n naught, and or xn equal to a n minus a naught x naught is the solution of the star. Okay? Know that A0 of n naught, A0 equal to, all right, may I say, know that when n equal n0, then a n0 minus n0, that is equal to phi n0 phi inverse of n0 equal I, sorry, or A0 is I, okay? So A0 will give you the identity matrix. So let's summarize what we really have done. If you have a system like this where A is a constant matrix, and if, let's make it the simplest case, if all the eigenvalue of A are distinct, then the corresponding eigenvector V1 all the way to Vk are linearly independent, and its solution can be written as phi equal Vi lambda I to the n. You form phi, and then you take phi inverse of n naught and define a n minus n naught equal phi n phi inverse of n naught, and then that would be the solution. For example, if n naught equals 0, then a n is phi n phi inverse of 0. Okay? Most of cases we'll take n0 to be 0. All right. So we did the easy case where the eigenvalues are distant. Okay, now I think my eraser needs to be changed, and I don't have a change to it. Can I use this one? All right. So sometimes an eigenvalue of A with multiplicity m, I mean, it's like lambda minus lambda naught to power n. This is something like that. Okay? So this is what it means. Okay? Does not produce m linearly independent eigenvectors. It may not. It may or it may not. So in general, if lambda minus lambda 1 to power n is a factor of determinant of a minus lambda I equals 0, and lambda minus lambda 1 to the m plus 1 is not, okay, then lambda 1 is, the lambda 1 is said to be an eigenvalue with multiplicity m. Okay? So let's take a look at case A. If it is possible to find n linearly independent eigenvectors vi I equal 1 all the way to k, all the way to m, for the eigenvalue lambda 1 with multiplicity m, then the solution will contain C1 V1 lambda 1 to the m plus C2 V2 lambda 1 to the n. Okay. All right. And all the way plus CK or CM VM lambda 1 to the n. Okay. All right. All right. Now, okay. All right. Now for case B, oops. Just a minute, guys. I don't know what I did. Oh, shoot. Oh, well. Let's take a look. All right. Um, B, if there is one eigenvector corresponding to an eigenvalue of multiplicity m multiplicity m, then m linearly independent solutions of the form phi1 of n equal v11 lambda 1 of n. Okay, and here we're taking to be lambda 1. Okay, phi2 of n is v21 n lambda 1 of n plus v22 lambda 1 of n. And phi m of n equal vm1 n to power m minus 1 over m minus 1 factorial lambda 1 to the n plus vm2 n to power m minus 2 over m minus 2 factorial lambda 1 to the n plus k m lambda 1 to the n. Okay, now the Vij are column vectors that can be found. And they are known as the generalized eigenvector. Okay, called the generalized eigenvector. And they are linearly independent. So I'm gonna do next, take a look at this, see what we did, and I'll explain to you what I'm gonna do next. All right. Now, let's I don't know what's going on with this. All right, this is do this and my the gas cap. All right. Now, again, let's take xn plus 1 equal a xn. Okay. Then, and then for illustration, of B, we suppose lambda 1 is an eigenvalue of A with multiplicity 2. That is m equal to 2. Okay? Then with only one corresponding eigenvector V. Okay? So let's assume we suppose lambda 1. So we know then phi 1 of n equal to V, right? Lambda 1 of n. All right? Now the question is, how do we do phi 2 of n? Because this is a 2 by, let's say this is m equal to 2. So we need phi 1 and phi 2. Those solutions belong to lambda 1 with multiplicity 2. Okay, so multiplicity 2 basically, so what you have is lambda minus lambda 1 to power 2 equals 0. This is what it means. All right? So we assume a second solution phi 2 of n of the form phi 2 of n equal v n lambda 1 to the n plus a p lambda 1 to the n. And this is, we're going to call 4.2.7. Okay. Now remember, we know V. This is V times N times lambda 1 to power N. So we know V. And we need to compute a P. Okay? Are you with me? Now, substitute here. So we know phi 2 of N plus 1 equal to A phi 2 of N. You see what happened? From here. Or phi 2 of N plus 1, V times N plus 1, lambda 1 N plus 1, plus a P lambda 1 N plus 1 equal to A Vn lambda 1 to the N plus P lambda 1 to the N. This is what both sides look like. Okay? So let's multiply it. So we're going to have A, okay? So let's A V N lambda 1 to the N plus A P lambda 1 to the N. Let's take this over there, minus Vn lambda 1 N plus 1 minus V lambda 1 to the N plus 1 minus P lambda 1 to the N plus 1 equals 0. You see what we have? Okay. So what I'm going to do is let's let us factor N lambda 1 to the N. Let's factor N lambda 1 to the N. What do we have? We have AV from here minus V lambda 1, that is from this. That's it. Correct? Do you see anything else? Minus Vn lambda 1 will have minus V lambda 1. All right. Now what is left? Lambda 1 to the N plus lambda 1 to the N. I'll have AP I should have another term. Did I miss something? Oh, AP minus V lambda, lambda 1, minus P lambda, minus P lambda 1, and that is equal to 0. Okay? All right. Okay. So n lambda 1, n is not 0. So we're going to have AV minus lambda, sorry, AV minus V lambda 1 equals 0. And we're going to have AP minus V lambda 1 minus P lambda 1 equals 0. But this is the same as A minus lambda 1I V equals 0. See, this is we know. Okay? This will give us V. But this one will tell us that A minus lambda 1I P equal to V lambda 1. Okay? Or lambda 1 V, it doesn't really matter. Which is lambda 1 V, because lambda is constant. So, hence, 4 point, this is called 4.29. 4.2.9 determines the other eigenvector P. Okay? There you go. And finally, the solution is xn equal to c phi 1 of n, c1 plus c2 phi 2 of n. This is phi 1 of n, and this is phi 2 of n. And that is your solution. And this can be written as phi of nc, where phi of n is where phi of, if this is a solution, where phi of n, where phi 1 and phi 2n are the columns of phi of n, and c is C1, C2. Okay, so now I'm gonna do an example. Okay. Any questions? Okay, let's take a look at an example. Consider the system. This is example 4.4. So let's take a look at xn plus 1 equal 3, 2, minus 18, minus 9, x1, x2. Okay? If we look at a minus lambda I, that is 3 minus lambda minus 18, 2 minus 9 minus lambda. That is 3 minus lambda minus 9 minus lambda plus 36 equals 0. Okay? See what we did? Now, if I simplify this, I'm going to get minus 27 minus 3 lambda plus 9 lambda plus lambda squared plus 36 equals 0. So I'm going to have lambda squared plus 6 lambda, okay, plus 9 equals 0. And that is lambda plus 3 squared equals 0. So we got lambda 1 equal minus 3 of multiplicity 2. All right? All right. Now let V equal V1, V2. So we need then A minus lambda IV equal to zero implies, okay, implies 3 minus lambda minus 18, 2 minus 9 minus lambda, V1, V2 equals 0, 0. And we have 3 minus lambda V1 minus 18 V2 equals 0, 2 V1 minus plus minus 9 minus lambda V2 equals 0. Okay? So now, if I take lambda equal lambda 1 equal minus 3, what will I have? So I'm going to have 6 V1 minus 18 V2 equals 0. That means V1 is 3 V2. And have 2 V1 minus 6 V2 equals 0. That means V1 is 3 V2. That's it. If I let V2 equal 1, then V1 is 3. So V equal to 3, 1 is the only eigenvector. Okay? Take a look at this, what we did. All right. So we need to find the second eigenvector. So we know V is the 3, 1. Okay. So let's come here. Okay. So we're going to use, so first of all now, phi 1 of n is V lambda 1 to power n. That is the 3, 1 times minus 3 to power n. So we know phi 1. Okay. So we're going to use now A minus lambda 1 I a P equal minus lambda 1 V. Equal to lambda 1 V, sorry. Okay. So where P is P1, P2. Okay. So we have a P. So we have, if you look here, these are the same equation. So we have 3 minus lambda 1 P1. So we have 3 minus lambda 1 P1. Okay. Minus 18 P2. Okay. This one is equal to, remember V is a 3, 1, is equal to 3 lambda 1, okay, and 2V1, 2P1 plus minus 9 minus lambda 1 P2 equal to 3 lambda 1 equal to lambda 1. Okay. So this is what we have so far. So this give us this one. Okay. Okay, so let lambda 1 equal -3. So we'll have 6p1 minus 18p2 equal -9. And we will have TP1 minus 6p2 equal to -3. Okay? So either equation if I set, you see these equations are equivalent. Just divide by 3 will be 2 minus 6 minus 3. So these equations are equivalent. So set P2 equals 0, the easiest one. Then 2P1 equal -3, and P1 is -3.5. Hence, the P equal to -3.5, 0. So we got it. Okay? Now, you don't need to take a P2 to be 0, take it 1. But you're going to have more terms. Remember, you are looking for a non-zero vector. That is a non-zero vector, even though it has one component 0. A zero vector means every component is 0. Okay, so now what is the solution? Phi2 okay. So what is Phi2 now? Phi2, so Phi2 of n is Vn lambda 1 to the n plus P lambda 1 to the n. That is P 3, 1, n times -3 to power n plus -3.5, 0, -3 to power n. Okay? All right, so what do we have here? If I factor 3 minus 3 to the n, if I factor -3 to the n, what do I have? I'll have 3n minus 3.5. Okay. And I have n. There we go. Okay. All right. So if I take phi to be phi 1 of n, phi 2 of n, that's gonna be, all right, I wrote it here in details. 3 times -3 to the n, okay, -3 to the n, and 3n minus 3 to the n, -3.5 -3 to the n, and n minus 3 to the n. There is your Pn. Okay. Now, if we are given xn naught equal to x naught, okay, then the solution is xn equal to Pn Phi inverse to n naught x naught. So you need to take the inverse. All right. So, and that is a n minus n naught x naught. Okay. So that is your, so basically, so an is an minus a naught is phi n, phi inverse of n naught, no, not x naught. Okay. So that is your an minus n naught. All right. So you need to find the inverse though. All right. To be able to find the solution. Okay, let's take 5 minutes break and come back. You have any like liquid glue? And All right. Now we're going to look on section 4.3. And this is called Putzer algorithm. Putzer is the name of the guy. It's capital P. Okay. So this algorithm gives us an regardless of the type of eigenvalue we have. Of the matrix A. Okay. So you see, before we were lucky. I mean, if all the eigenvalues are distinct, then we automatically have, if we have k distinct eigenvalues, automatically we are guaranteed k eigenvectors that are linearly independent. Now, in this immediate previous discussion, we looked at case B, where let's say lambda 1 has a multiplicity m less or equal to k, the size of the matrix, then you're lucky if that eigenvalue produces m linearly independent eigenvectors. But if it did not, then we resorted to generalized eigenvectors. And that is a little bit difficult. So now we're going to look at this Putzer algorithm. Regardless of what type of eigenvalue A has, you can always find the matrix AN. Okay, so here's what it says. Suppose A is a k by k constant matrix with eigenvalues lambda 1, lambda 2, lambda k that may come in any order or multiplicity. Or multiplicities. Okay. Suppose mu1 of n, mu2 of n, mu k of n satisfy the following relation. The following relations: mu1 of n plus 1 equal to lambda 1 mu1 of n, and with mu1 of 0 equal 1. Then you have a mu j of n plus 1 equal to lambda j mu j of n plus mu j minus 1 of n, with mu j of 0 equal 0 for j equal 2, 3, all the way to k. Define the matrices D0, D1, dk recursively by D0 equal I, and dj is the product k equal 1 to j a minus lambda k of I for j equal 1 to k. Then this is the conclusion. An equal to j equals 0 to k minus 1 mu j plus 1 to the n dj. Okay? And that is 4.33. I am going to skip the proof. The proof is in the book. Instead, I'm going to concentrate on an example. So regardless, so for example, if you have A that is 2 by 2 matrix, and if you have, let's say, determinant of A minus lambda I equals, say, lambda minus 3 squared. So you have lambda 1 equal to 3, lambda 2 equal to 3. You see how we are numbering them? And that's how we are numbering here. Lambda 1 equal lambda 2 equal lambda k. So in other words, if determinant of A has lambda minus lambda, whatever you want to call it, what do you want? Lambda minus lambda 0 to power m equals 0, then you're gonna go lambda 1 equal lambda 0, lambda 2 equal lambda 0, all the way to lambda m equal lambda 0. You see? That's how you label them. All right. So again, as I said, the proof is in the book, a little bit complicated, and I'm not gonna go over it. And for those who are math major, you should go over the proof. Okay? Instead, I'm gonna do a complex example that explain the material. All right. So that is the theorem. And remember, the mu are related to the lambdas. You see that? And it does not really matter how you label your lambda. Okay? All right. So let's do an example. solve, and this is example 5.42. Sorry, 4.5. Xn plus 1 equal to 2, 2 minus 1, 2 minus 1, 2, minus 1, 2, 2, x1 of n, x2 of n, x3 of n, with x0 with x of 0 equal x0 equal to 1 minus 1, 2. Okay? This is gonna be a long example. So the eigenvalues, so A equal to 2 minus 1, 2 minus 1, 2, minus 1, 2, 2 has the eigenvalues 3, 3, and minus 3. So I have decided, so we're gonna set lambda 1 equal to 3, lambda 2 equal to 3, and lambda 3 equal minus 3. Okay? So far, so good? Okay, so now you see what we need to compute is, let's compute the D0. Okay, K equal 1 to J. Okay? So we're gonna using all right. So we have D0 equal to I, and dj is the product of j equal 1 to k. K is a 3. So will be 3, will be k minus 1. Okay? I'm looking for my dj. I'm looking at the statement of the theorem. I can't find it. Oh. K equal 1 to j. All right. So this is gonna be, if I look at this one, let's see, where is it? Where is it? Where is it? A minus lambda ki, okay? All right, so that is j equal 1 to 2, a minus so a minus, sorry, this is lambda j of I. So okay, so this is gonna be dk here, sorry. Okay, and k equal to, so for k equal 1, d1 is product of j, this is j equal 1, k, okay, let's see, maybe I messed it up. Okay, let's see. So we have, what is this stupid equation? Oh, okay. So the formula is dj k equal 1. Let's go like this route to j a minus lambda k. Okay. And j, so this is j equal 1 to k. So for j equal 1, j equal 1, d1 is k equal 1 to 1, a minus lambda 1 I, that is a minus lambda 1 I. Okay? So this is what I have. Okay, let's see. And E2 is k equal 1 to 2, a minus lambda k I. All right, k equal 1 to 2. K equal 1, this is a minus lambda 1, lambda 1 I. Okay, and times a minus lambda 2I. Well, I1 equal I2, lambda 1 equal lambda 2 equal to 3. So this is 3 minus I squared. Okay? So here, let me go back to the formula. Where it is, where is it? dj k equal 1 to j a minus lambda ki. All right. Okay. So this is our DJ. So we need to compute them though. Okay, so we know A minus lambda 1 I. We can do that. D0 is I, A minus lambda 1 I, and then A minus 3I squared. I looked at, so D0 is 100,010,001. And if you compute D1, you're gonna get -1, 2, -1, 2, -4, 2, -1, 2, -1. D1, A minus lambda 1 I, and D2 is 6 -12, 6 -12, 24 -12, 6 -12, and 6. So these are the D0, D1, D2. Okay? So you compute those, and all right. Okay? Now we have to solve the system. Now we need to solve okay. So now we need to solve mu1 of n plus 1 equal to, you see it? Lambda 1, mu1 of n, that is 3, mu1 of n, and with a mu1 of 0 is 1. Well, that's easy. So the solution un is 3 to the n mu1 of 0, okay? But the mu1 of 0 is 1. So this is 3 to power n. Okay? Or now mu2 of n plus 1 is 3 mu2 of n plus mu1 of n. That is 3 mu2 of n plus 3 to power n, and mu2 of 0 is 0. Okay? Now, you recall the formula. Recall that if you have xn plus 1 equal axn plus gn, then the solution is xn is a n minus n naught, x naught plus r equal n0 to n minus 1, a minus r minus 1, gr. And so here a is 3 and g of n is 3 to power n. So mu2 of n is a to power n minus naught, 3 to power n minus 0, because n naught is 0, plus r equals 0 to n minus 1, 3 n minus r minus 1 times 3 to power r. Because g is 3. Well, 3 to power r, 3 to power r cancels out. This is 3 to power n, 3 to power r minus 3 to power r. So this is plus r equals 0 n minus 1, 3 n minus 1. That is 3 to the n plus 3 n minus 1, sum r equals 0 to n minus 1 of 1. That is 3 to the n plus 3 to the n minus 1 times n. Okay? Now, oh, I forgot to write mu2 of 0 here. So that will be 0. That is 0. That is out. Because mu2 of 0 is 0. You see that? So we have n3 n minus 1. Okay. So this is a mu2. Now, a mu3 of n plus 1 equal minus 3 mu3 of n plus n times the 3 n minus 1. Okay? And again, I have mu3 of 0 is 0. Okay? So you have a mu1 of n with 3 to power n. Mu2 of n is n 3 n minus 1. Okay, so this is gonna be mu3 of n is going to be minus 3 to power n mu3 of 0 plus r equals 0 n minus 1, 3 n minus r minus 1, or minus 3 times r3 r minus 1. Okay? So we're gonna this is 0. So this is r equals 0 to n minus 1. Now we're gonna take minus 3, okay? to power n minus 1 so this is gonna be 1/3 times -3 n minus 1 times r equals 0. This is r minus 1 to power r. Because I can simplify by the r minus 1. Okay? You see, -3 to power n minus r minus 1, I can write -3 to power n times -3 r minus 1. You see that? So I can write this as r minus 1 as -3 to power n times -1 minus r minus 1 times times 3 to power minus r minus 1. Okay? And so when you simplify this, so when you have -3 n minus r minus 1 times 3 to power r minus 1 times r, okay? So we're gonna write this as -3 to power n times -1 to power -1 times -1 to power minus r times 3 to power minus r minus 1, okay? And 3 to power n minus n times 3 to power r minus 1, okay? So the 3 to power r cancel out, okay? And then this is what you're gonna end up with. You will end up with this one, r to power -1 to power r. Now we need to do an evaluation. We need to do summation by parts here. We need to do summation by parts to compute it. So let me finish it next time because it's a little bit complicated. I want to get this example finished so you can understand it, because the computation is not easy, so you know how it's done. So I'm gonna stop here and I will continue with the mu3 next time and find the matrix AN. Any question, email me or text me or anything.